In this video, we're going to look at how we would analyze data when we're looking for the difference of means. For context, we're going to be looking at a study where the blood plasma level of ascorbic acid, much better known as vitamin C, is being tracked in two groups of pregnant women, one group smoking, one group not smoking. As we go through the analysis, having just been given a data file, we're going to be looking at ways to display the information, either summary information about how many samples of each kind, and also some graphical comparisons as well. And then we're going to end, or along the way, do the final p-value computations for whether these two groups are different or not. Related to the graphing side, the Seaborn package is going to be very useful for us in this kind of analysis where we have two groups with continuous data being under measurement, and we'll see that in action shortly. So first thing we're going to do is load our data and show the first 10 lines of it, or first 5 lines of it here. And what you see is we've got ID numbers, we've got smoking status, and some kind of measurement of the ascorbic acid level, milligrams per deciliter. Of course, that doesn't tell us too much, so we might want to know just how many smokers there are and so on. So for that, we would use the smoking status, and we would say count the values, or value counts rather. And that'll tell us that we have 25 smokers and 17 non-smokers. Perfect. All right. And again, if we want to make everything output in one block, we use that print convention. There we go. So what kind of information do we have here? Well, we have two groups of patients, two groups of study members, smoking and non-smoking. And we have a measurement that's continuous for each one of them. We have a numeric value. And so if we go over to the convenient flowchart for how to analyze this kind of data, we'd be scoping down first continuous variables, numbers of samples, 1, 2, or more. Oh, we got 2. Actually, I'm just going to go to the next one. We'll see the guiding here. We got 2 different samples, the smokers versus non-smokers, and we want to compare their means. They're independent in the sense that it's not the same woman in both studies. And we don't have any information about the standard deviation for the population. So we go straight down to the pooled t-test as a way to assess, working our way back up here, whether the two means are different. Do the two groups have the same level of ascorbic acid concentration if they're smoking and non-smoking? Okay, well, how do we figure that out? First off, I think it's helpful to see a graph, because whenever we have data like this, we can just look at the numbers, but that's not as intuitive as a pictorial representation. So I'm going to introduce one of the Seaborn technologies that is going to help us a lot here. So SNS is just a shortcut for the Seaborn library. And there's this handy generic plotting thing called cat plot. And the idea there, it's sort of it's for categorical data, or data with categories in it. And so the smoking status is our category here. The idea is we want to do things, plot things broken up into groups. So is it going to work? No, we have to type it in. So what we're going to do, first example, just work through it, and then you'll see the logic or the structure behind it. And here's a little tough to copy, so I'm just going to paste it. And data equals, we call the data, very originally, data. So what this does is a scatter plot, essentially, of the ascorbic acid levels in a column, though, separated by the status of smoking or not smoking. So this is a great way to quickly show the data. And just looking at it right now, it doesn't look like there's a lot of difference between those two groups. There's a couple more extreme values here, but anyway, it doesn't look like there's a big difference. So going to our null hypothesis up here, just to put it in for consistency with our other approaches, the null hypothesis here would be that both groups have the same mean level of ascorbic acid. Or if you like, that smoking has no effect on ascorbic acid levels. Levels in pregnant women. There we go. Now again, you can think of this as a sales pitch that helps give you the context of the p-value when we get to that later. But basically the null hypothesis is someone telling you, smoking, not smoking, whatever. You can almost think of this in some sense as a conspiracy. Yeah, it doesn't matter. Smoking doesn't hurt anybody. It's fine. So that's the claim. Smoking doesn't do anything. Smoking, non-smoking, same results. For ascorbic acid. A whole bunch of other health things separate, but for ascorbic acid levels in this study, there's no effect. And honestly, looking at the graph, we think, probably no probably is no effect, but we need to back that up with some evidence. But before we do that, I just want to show a few variations on this plot here. So this is a little untraditional in terms of plotting. It's not the first thing you learn in plotting, because it has this sort of jittering of the data points to make them separated visually. Some people like it, some people don't. A more traditional thing to do is to make this a box plot. And you can do that easily just by changing the kind. So there's an option for kind here, and you just say box. And all of a sudden you have a box plot. Now notice there's a different take on this. You can certainly see that the range is different for the two groups, the smoking versus non-smoking, but you can also see that actually the median is different between the two. So maybe there is actually an effect happening here. We'll have to dive in further and do some statistics to determine that reliably, but there's a little more evidence for it here. I'm going to throw in a third variation on this because I just thought it was so neat when I found it, and that was called the violin. You'll see why in a second. What this does is, let's turn on the data points as well here. So the violin model basically does a smoothed histogram of the data set on each column here. So you can see the bars here. This is the box plot hiding inside, but the curves around that are capturing the density of the points here. So there's a big cluster of things here in the middle. You see that there. In this data set, you can see there's a big cluster at the bottom, but no matching thinning out on this side. Well, you see that here. There's this large bulge going on this side, and then it thins out. So essentially you get a combination of the box plot and the histogram together. And sometimes that's really useful. If you want to add one extra variation on that, there's an extra example, and all of this is taken straight from this tutorial. So this is nothing I've discovered independently. You can add every data point specifically or explicitly rather in this graph as a horizontal line. So you can actually see there's a bunch of dots here around 1.3, 1.2, 1.3. Yeah, that's that cluster right there. And then there's a scattering of points further down around 1. And so you get a different kind of information with this plot. I'd say this is probably very far off what most people would feel comfortable putting in a sample graph or something that you'd publish. This I think is more easily understood, but if you really want to stick with tradition, then the box plot is for sure something that everyone who took first year or introductory stats would recognize and be comfortable with. Okay, so that's our plotting. Now we need to get to the statistical analysis. So what we're going to do is, what we're going to have to do for the analysis is break the data up, unfortunately. We actually have to make two separate data sets. So the way we're going to do that is thinking back to week 1 of the course when we had to do subsets of data. So we're going to take our smoking status, and we're wondering whether it equals smoker. If you can't remember, you go up to that values list that we did earlier. You can see smoker's one of the options. And I'll put that here. And what we're going to do is just take the ascorbic acid column out of that. So I'll parse that in a second. There's our ascorbic acid. So let's actually do this. Just delete this temporarily. So what this would do is take the data smoking status, so all the columns in the smoking status, all the data points in the smoking status column, and find those that match the smoker. So that'll be a binary list, and it'll have 25 yeses and 17 nos, or trues and falses. And then we add this extra layer around it, which is the subset. So we say, I'm going to take that data, and I'm going to use it to sample the rows of my data set, so I only get the smokers. And then once I have the smokers, I'm just going to keep their matching readings of vitamin C, ascorbic acid. And let's just see how that works. So I'll do that. And what we see is starting at 0, going to 24, so 25 total values, we have all these ascorbic acid measurements. Perfect. Now, of course, we're going to want to do the same thing again, but with the smoking status, which is non-smoker. And just be careful with capitalizations. Again, I have to be careful with capitalizations. It's a lowercase s. So put that in there. And let's comment that out for a second. We can't indent, of course. There we go. So these are the data points that come from the non-smokers. And then we just store those as two different data. I'm just going to call them data 1, data 2, because we're not going to hold on to them for long as separate entities. So we get two different data sets. This is our, going back to the discussion of what kind of statistical test to use, this is our two independent samples. So now we have a sample of 25 smokers, or 25 smokers, 17 non-smokers, and we're going to do the pool t-test on that. A little Googling for how to do the t-tests, we'll find that we're looking for, in SciPy, in statistics, we're looking for the t-test, and indication. There we go. So I'm just going to do a quick run of that for the help lookup. And you see it's got two inputs, A and B, which are the array-like things. So again, this is the two samples. And we're not going to worry about anything else. Equal variance would be something, if you took more stats or went back to your old stats, you would be able to toggle that on or off. For now, we're going to assume everything's fairly vanilla. And what does it return to us? It returns the statistic and the p-value. So we're just going to run this, comment that out, but we're going to have the t-value and the p-value equals this with the data 1 and data 2. And of course we want to print something there, so we're going to print the p-value, percent point 3f, and we're going to format the p-value. Bracket. That looks good. Perfect. Okay. If you want, you can print the t-score. That's like the normal z-score. Extreme values above 2 is usually suspicious, that kind of thing. But for us, for now, this is the result we need for the moment. We have a p-value and it's a probability. So think of this as 13%, 14%, or 13 times out of 100. It's another way to think about this. And it's related to the null hypothesis. If both groups, someone's telling us the story, both groups have the same level of ascorbic acid, and we're like, okay, sure, that's a claim. Now let's think it through, and we do our data collection to test whether they're telling the truth or not. And what we find out is, if they're telling the truth, then we would see this kind of outcome 13 times out of 100, 14 times out of 100. That's not unreasonable, you know? If it was 1 in 100, I'd be more worried. And this again goes back to the usual cutoff for p-values of 0.05, you know, 5 in 100, 1 in 20. That makes people suspicious. This is not strong evidence that the statement that these are the same is a lie, is a mistake. It's certainly possible to have gotten this data set collected, because it could have happened, you know, to have a difference of means here that we see here, on average 13 times out of 100, if we kept repeating this experiment, and the person was telling us the truth. So our conclusion here would be that based on a p-value above 0.5, 0.05, we would not reject the null hypothesis based on this data set. Again, we do see a difference, so we might be thinking, well, maybe I just needed more samples, because the more samples you have, the finer distinctions you can make. You might think that this is actually fine, that smoking just doesn't affect ascorbic acid levels. That's true. That may be true too. But whatever your suspicion is, this data set does not provide compelling evidence to change your mind that the smokers and non-smokers have different levels. Here they look similar enough, and the statistics bear out that it's not unreasonable that this could happen, this data set could arise, this difference in means could arise, if there actually is no difference going on. So our conclusion is, based on this data, we'd stick with the null hypothesis for now, until more evidence comes to light.